Hello everyone. Let's start with a simple but powerful idea, the center of mass. Imagine holding a seesaw with two friends of different weights. Where will it balance? Closer to the heavier friend, of course. In physics, we capture this balance point mathematically. If two particles of masses m1 and m2 are placed at positions x1 and x2 along a line, the center of mass lies at a distance x, given by the formula. X equals open bracket m1 times x1 plus m2 times x2 close bracket divided by m1 plus m2. If both masses are equal, the center of mass falls exactly in the middle. But if one is heavier, the balance shifts towards it. As you can see in the diagram, point C lies closer to the heavier mass. Now, what if we had not two, but many particles? Imagine beads strung along a line, each with different weights. Where is the balance point of the whole system? The answer is elegant. For n particles, the position of the center of mass is x equals the summation of mi times xi divided by the total mass m. Here, the denominator m is the sum of all the masses, while the numerator adds up their mass-weighted positions. This tells us the center of mass is really the average location, but weighted by mass, not just by count. It's the point where the whole system would balance if placed on a knife edge. Things get more interesting when particles are scattered on a plane. Imagine three marbles placed at the corners of a triangular board. Naturally, you might wonder, where is their balance point or center of mass? Suppose the marbles have masses m1, m2, and m3 located at coordinates x1, y1, x2, y2, and x3, y3. The coordinates of the center of mass are written as capital X and capital Y. Capital X equals m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Similarly, capital Y equals m1 y1 plus m2 y2 plus m3 y3 close bracket divided by the total mass. And here's a neat result. If all the marbles have equal mass, the center of mass lies exactly at the centroid of the triangle, the special point where the medians intersect. Isn't that beautiful? The geometry and the physics come together perfectly. Let's now step into 3 dimensions. Imagine particles floating in space, like stars scattered across a galaxy. To describe their balance point, or center of mass, we now use 3 coordinates, x, y, and z. Capital X equals the summation of mi divided by the total mass. Capital Y equals the summation of mi divided by the total mass. And capital Z equals the summation of mi divided by the total mass. But instead of writing 3 separate equations, physicists prefer a much more elegant way, the vector form. We write capital R equals 1 over m times the summation of mi. Here, Ri is the position vector of each particle and capital R is the vector pointing straight to the center of mass. Notice the beauty of this formulation. A single compact vector equation works for 1 dimension, 2 dimensions, or 3 dimensions all at once. Now let's move from individual particles to real solid bodies. Think of a rod, a disk, or even your smartphone. These aren't just a few particles, but billions of atoms packed tightly together. We describe such cases as a continuous distribution of mass. To locate the center of mass, we imagine breaking the body into tiny elements of mass, written as dm. When these pieces become infinitely small, our summations transform into integrals. So, capital X equals 1 over m times the integral of x dm. Similarly, capital Y equals 1 over m times the integral of y dm. And capital Z equals 1 over m times the integral of z dm. In elegant vector form, we write capital R equals 1 over m times the integral of r dm. This compact formula works for any solid body. And here's the best part, although integrals can look complicated, symmetry often comes to our rescue. For many regular shapes, like spheres, rods, or disks, symmetry makes finding the center of mass straightforward. Symmetry is a physicist's best friend. Take a thin rod. For every mass element at distance plus x, there's an identical one at minus x. Their contributions cancel, leaving the geometric center as the center of mass. The same is true for homogeneous rings, disks, or spheres. For every piece at position x, y, z, there's another at minus x, minus y, minus z. That's why their center of mass lies at the geometric center. So next time you hold a ring or a ball, remember, their balance point is right in the middle thanks to symmetry. Let's solve a real example. Suppose we have three particles placed at the vertices of an equilateral triangle of side 0.5 meters. The masses are 100 grams, 150 grams, and 200 grams. Step 1. Total mass is 100 plus 150 plus 200 equals 450 grams. Step 2. X coordinate of com equals open bracket 100 times 0 plus 150 times 0.5 plus 200 times 0.25 close bracket divided by 450. That gives 0.5 meters. Step 3. Y coordinate equals open bracket 100 times 0 plus 150 times 0 plus 200 times 0.25 root 3 close bracket divided by 450. Simplifying, we get square root of 3 over 9 meters. So the com is at coordinates 0.5 comma square root of 3 over 9. Notice in the diagram, the point lies closer to the heavier mass at vertex B, not the geometric center of the triangle. So, to sum it up, the center of mass is the balance point of any system of particles. It is found by taking the mass-weighted average of positions. For continuous bodies, we use integrals instead of summations. Symmetry often allows us to identify the center of mass quickly. For rods, disks, spheres, and other uniform bodies, it coincides with the geometric center. And as we saw in the triangle example, the com naturally shifts toward heavier masses. This simple yet profound idea lets us treat even complex systems as if all their mass were concentrated at a single point. I hope this gives you a clear and confident picture of the center of mass. In the next session, we'll explore how this point actually moves when external forces act, the motion of the center of mass. See you then.